Hi, and welcome back to another LeetCode problem. We're looking at a medium one, LeetCode 199, binary tree right side view. We're going to do our usual, read through the problem description, check the constraints, the examples, come up with a solution in our mind, make a runtime and space complexity analysis before we write a single line of code, and then we try to implement our idea. And yeah. And hopefully it all works out without any errors or mistakes. So let's dive into this. So we're given the root of a binary tree. Imagine yourself standing on the right side of it. Return the values of the nodes that you can see ordered from top to bottom. We will have from 0 to 100 nodes. So 0 means we can have an empty tree. And then we have node values between -100 and +100. So let's have a look at one of the examples. So here we have a tree, and the right side view is what we see when we stand here and look at the tree. So yeah, 1, 3, and 4 is what we see, and we don't see these other nodes because they're behind the right side branch of that tree. Here we have another example. Well, so this is interesting. So here we see that the right branch stops here, and now we can see the other nodes of the left arm. Okay. And the third example is, this is a tree that has a root node of 1, no left child, but a right child. So we should see 1 and 3. Even if the left child and right child were swapped, we should still get this as the output, I suppose. And oh yeah, and when we don't have a tree, when we get an empty node, we return the empty list. Nice. All right, so I think, so we could approach this, well, I think we have to visit all of the nodes. So we will have at least a linear time in the number of nodes, time complexity. We will also need to store the result, and the result is dependent on how high the tree is. So we have at least O of H space that we're going to need for our implementation. That is the minimum H space. And now there's different ways of how we could approach that. I think one that might be quite easy to implement is if we just traverse the tree level order, and then we always take the last node from each level and add that to our result. So we would first, we would have probably a first and first out data structure. We would put in the root node, and we would iterate while we still have nodes to process. And so we put in the root node, and in a loop, we're going to remove the first element from our data structure, which in this case would be the root. And we would append its left and then its right child back into the queue for processing them next. And at the same time, since the root is the first and the last, also the last element that we pop out of our queue in that level, that goes into our result. So in the next iteration, we have the nodes 2 and 3 in our queue. We process node 2, and we place its children, which is only 5, back into the queue. But because the queue has not fully been processed for that level, we don't append the 2 to our result. Instead, we then process the 3. We know that the 3 is the last node in this level, and we append the 3 to the result. And of course, put the 4 as the into the queue for processing in the next level. So I think, yeah, I think that's a solution that we should implement. So let's do that real quick. Now in Python, there's a data structure for the FIFO, which really supports, O of 1, removing of elements from the top and adding elements to the end, unlike an array, which is an O of n operation when you try to remove an element from the front of the array. So I'm just going to import that from collections, import the deck. And we want to initialize that here, and we're going to place our root node in it. Right. So while we have elements in our queue, we're going to iterate over all of the elements that we currently have. So for, and we don't actually have to keep track of the index, so we're just creating a loop that loops n times until we've reached the end of the queue. For in range length of the queue. And we're going to pop up the node that is in the queue. And we're going to use the pop left method, which removes one element from the beginning of the deck. So node. Now we have to deal with the edge case where root is none, right? Where we have an empty tree. So we have to do a check here. If not node, we're just going to continue. We're just going to ignore that node. And let me also quickly add our return value. And I'm just going to call this area result. And it's going to be empty by default. So if we have this case, that means we're putting a none value inside our deck. We're actually entering the while loop because we have one element in it. And then we're going to iterate over that one element. We are popping it out, but it's none. So we're going to ignore the processing of it. We exit the for loop, and then the queue is empty, and then we return our empty result. So that's the edge case managed. Now, if the node is not none, well, what do we have to do? Well, we have to add the left and the right child back into the queue, right? And we don't really care if it's none or not, because we already have the check of whether it's none here. So we just add them. The queue append node.left. We also do queue append node.right. And now the only thing that is missing is that we need to keep track of what was the last node that was not none in the current level. And last node. And we're going to do this. And we are going to do this. So we're going to remember the last node that was not none, right? And yeah, and then when we exit the for loop, all we need to do is we need to check if last node, because it could be none, right? In the, let's say the last layer is, if we reach the last node here, we will still add its left and its right child. So none and none are inside our queue. So we're still going to process all of these elements in there, but they're all none, so nothing happens. And that means that our last node will also be none, and we have nothing to add. But if it's not none, we have to add its value to our result. Nas.val, right? Yeah, .val. That's what we have to add. And that should be pretty much it. Now, because we're doing a level order traversal, and if the tree is fully populated, that means we have n's. If we have n nodes in the last layer, we would have n squared nodes in the entire tree. So actually the space complexity is also dependent on how many nodes we have in the tree. Let me think. Yes, so the last layer would be, actually it would be square root of n. Would it be square root? I have to think about this. Let me see. So if I have a binary tree, so if 1, then 2, then 4, then 8, then 16. And how many nodes do we have in total? Well, that's, how much is it? 12, 13, 14, 15. So we have 31 nodes in total. And we have 16 in the last layer. So that means that the last layer is actually, it's kind of like n divided by 2, roughly speaking. So it's still linear in the total number of nodes in the tree, the last layer. So our space complexity is actually also O of n, right? So let's see if this this solution works. Let's run the test case to make sure that we don't have any syntax errors, but we do. From collections import the deck. No, that's not wrong. So I typed what I said, but it should have been this. Of course, this is a typo. It should be result. There you go. And all cases are accepted. So let me submit it to see if there are edge cases that we are missing, but no. So this works well. I think we should now try to optimize this in terms of space complexity. There must be a way of how we can make that simpler for us, because, or is there a way or is there not a way? Well, I think there is, because right now we're using a depth first search. So our level order traversal is a depth first search through the tree. We'll always hold all the nodes of the next level in memory. That's why we have the space complexity. What if we could change it to a depth first search? Then at most we will have O of H nodes that we have in memory at any given time. So I think we should implement something like that. And level order traversal, I really like that. I mean, you can implement it also in a recursive way, but I feel like level order traversal lends itself to being implemented iteratively, whereas a depth first search is typically more elegant when you implement it recursively. So I would like to try a recursive approach with a depth first search. And well, the problem that we need to solve in this approach is, how do we know at which position the node is that we're currently visiting? So how do we know how this node number 4 is relative to possible other nodes that could be in the same level? Because we don't hold them in memory while we're traversing the entire thing, but we still need to be able to associate, let's say, a level index or an index on that level to the node, so that we can compare its index to other nodes that might be in the same level. And in the end, we're going to choose the one that has the lowest index, right? So if this is the root node and it has index 0, this would be on the level number 1. This is level 0. This is level 1. This is level 2. So at level 1, the position of this node would also be 0, because it's on the position that's all the way to the right. Now that node would be at position 1, right? So this would have a higher position value in the same level. Now if we go one level deeper, the 4 would also have an index of 0 inside of its level. The left child of 3 would theoretically have the index of 1. Then 5 has the index of 2, and the missing left child of node 2 would have the index of 3. So we need to find a way of how we can calculate that index when we do a depth first search. And I think the idea behind that is actually quite simple. So what you do is, when you traverse the tree, you always pass in a node and its position in its position in its own level, the index in its own level. Now when we go to the left, to the right, all we need to do is we need to multiply that position by 2. And if we need to go to the left, we need to multiply that position by 2 and add 1. The reason is that we have a branching factor of 2. So that means in each next level, you have twice as many nodes in theory and as before. So you can just multiply the index by 2 and you wouldn't change the order at all. You just need to take care of the fact that you now might be going right or left. So you add a +1 to use the free space that was opened by multiplying the previous index by 2, so to say. I hope that kind of makes sense. If not, maybe just look at the code, how I'm going to implement this. Maybe that'll make it a little bit clearer. So yeah, let's get rid of our deck. We're going to have a little helper method. A depth search helper, and that one takes a node and a position. position value of that node. Right. So that's what we're going to do. And we're going to have our result array, right? And at the end, we're going to return it. Cool. So the first thing that we need to do, we also need to pass in the current level where we are. What is the current level? Level, node, and position. So we will call our helper method. And we could also make it return the helper and return the result in here. Helper, so we start at level 0 and we start at the root and the position is 0. That's our initial, that's our input. So if not node, that is our, how do you say, what do you call it, terminating case, or that is the case that ends the recursion. So if node is none, there's nothing for us to do. We just return result, right? Or we write it like this. If node, then we're going to do a bunch of stuff. Otherwise, we're just going to return the result. So that takes care of the edge case where the node is none. Right, it's this case. If it's none, we're not going to modify the result array. We're just going to return it. So it's an empty array. Everything is as we want it to be. Great. Okay, so now what we do? Well, we have to check, do we need to expand our array or not? Because if the root node has something, our array has nothing. So we need to create an entry in our array for that level. So if level is larger, larger or equal to the length of our result, because level is going to be 0 in the beginning, and the length of our result as well. So if it's equal, just equal is probably enough. So if it's equal, we need to append something to our result. And let's append. Well, what are we going to append? Well, we're going to append the node value, but also its position. That's what we will do. And otherwise, we have to compare our current node position at that level to the one that is already in the result. So what we will do, we will access the node at level. And if result at level, and it has a node, and now we're going to access its positional value. And the positional value is as index 1, so this index 0, this index 1. If that position is larger than what we have here, than this position, then we actually need to update it. So in that case, what we do is we set this to the current node that we're looking at. Yes. And we can also simplify this a little bit, like so. Zero and 1 position, yes. Yes. Okay. Or we could write it the other way. So if the position we're currently is smaller than the one that we currently have, doesn't matter, it's the same thing. Whichever you find more expressive. And that is that. But now we have to do the recursion. So we're going to do the DFS helper level. We're going to increase the level. We're going to go into the left node. I said we're going to multiply our position. And we also do this for our right node. So we do one level more, right node, but then we don't add the +1. And yeah, and maybe we add, let me just see. If we first go down the right path, It probably doesn't really matter much, but yeah, in which order we go down. That's not really relevant. I just like it like this. First go down the right, then down the left. So that's what we do. And now, so this is the right, this is the left. Yeah, and now everything should work out fine. But in the end, what we have to do is we have to change our result to not include the positions, right? So finally, what we'll do is we say result equals, and now we look at the value for value and position in result. We don't really need this here. Yes. Now, if the result is empty, there's nothing to do here. So I think everything should be fine. Okay, I'm brave enough to run through the tests and lazy enough to check for syntax errors. Hopefully we didn't make any. All right, so it seems that all our test cases pass. And yeah, let's submit it. See if it really passes all the test cases. And yeah, there, so, and Bob's your uncle. So, all right, so just to summarize, level order traversal with an iterative approach gave us linear space, and depth first search approach gave us an optimize of H space complexity. And yeah, that's it.